an image here, we have to put it into the imaging plate reader. There is a reader for that, and then the image comes up on the monitor, and this is what we have in our room. With a digital detector, it's built into the table, and with digital radiography, the image immediately comes up onto the monitor. There's no reading of the detector with another device. Okay, so either way, the ultimate image is the same, whether it's CR produced or DR produced. Okay, so as an instructor, I have to remember that there are some things that are going to be different with film versus CR and DR. But one thing that is the same, regardless of CR, DR, film screen, is that what you may in time control, and that's the quantity of electrons boiled off at the filament to produce X-rays. So you want more X-rays, you use more MA. How much more depends on what body part you're taking an X-ray of. So you're doing a hand, you use less MA. You're doing a hand, and MA and time are married. Okay, they're married. So if you want to double the exposure to a patient, let's say you're given a certain mass, and you want to double the exposure to a patient, you can do one of three things. You can double the mass, you can double the MA, or you can double the time. Any of those would work. Okay? So when you're looking, and I'm just going to caution you now, when you're looking at the control panel, when you're looking at a test, when you're looking at a quiz, when you're looking at the homework I'm about to pass out to you, don't get MA and MAS confused. Okay, they're not the same thing. Okay, MA in time controls the quantity of electrons, and it also therefore controls the dose to the patient, the entrance skin exposure. Okay, so if doubling the mass or doubling the MA or doubling the time doubles the exposure to the patient, what kind of relationship is that?
Direct?
It's a direct relationship. And doesn't it make sense? More radiation, more exposure to the patient. So if you're given a statement like this, and this is on page 238, as I said, the reading assignment is very short for this. You have 200 MA, and we see this is MA, it's not MAS. Your MA is going to be something like this, everybody. All the way up to maybe 1,000. Okay, your MA stations are going to be in hundreds. In that back room, we played around it the other day. There was like 238, 176. It's going to be in the hundreds like that. Your time, this is MA, your time is going to be, it can be in three different things. I grew up with fractions, so we had 1/60th of a second or 1/120th of a second. So this was in seconds. Then we went to decimal, so it would be 0.01 second, 0.05 second. As an example. Now, the newer equipment is in milliseconds. So this would be, and I need you to know how to do this. So from seconds to milliseconds,
10
it would be
milliseconds.
10 milliseconds. How do you know that? You just move the decimal over. Milli is 10 to the minus 3. Move the decimal over 3 places. So what would this be in millisecond?
50.
50 milliseconds. Just to complicate things, okay? So how do you find the mass of something? How do you find, if you're given a certain MA and you're given a certain time, how do you find the mass?
Multiply
You
it.
just multiply it. That's right, you just multiply it. That simple. However, what if you're giving a certain MA and 50 milliseconds?
Convert that to those.
That's right. You multiply, but you move that decimal
3 spots.
3 spots. So it's not MAMS, it's MAS. Okay? So there's a little bit of conversion there that I need you to be okay, comfortable with. And I've got some practice problems for that, just to make sure you know how to do that. So if you run into any trouble with it, you and I can muddle through it together. This is me. I was raised with fractions.
Ugh.
I know, see, I told you I'm old. Okay, raised with fractions. And then I remember going to decimals. Okay, I mean, these aren't hard ones. Do you realize if you're off one decimal, that's a factor of 10 times off the mass? So I would be like, oh, and then now, forget that, now we're in milliseconds. So now you've got one more thing. And someone said, we were practicing doing some of this with the control panel. You don't carry your calculator around and figure out your mass. So if someone says, oh, use 70 mass, what MA station are you going to use and what time station are you going to use? And you know what? There is another button, just like on our machine. There's a mass button. You want 70 mass? Hit your mass button and go to 70. There you go. It's like, well, then why do we have to? Okay, but we'll get there. I'll tell you why. Okay. Where am I? Okay. Okay, so going back, this is not 200 mass. This is 200 MA, okay? We have the entrance skin exposure is 750 milli-R. What is it at 500 MA? Okay, first of all, what would you expect the exposure to be, more or less?
More.
More. Wouldn't it? If you're at 200 MA and that produces, what does 200 MA do? It produces, let's just say, 200 electrons as a filament to produce 200 X-ray photons. It's not like that, but as a visual. So do you think 500 would give you more electrons, more X-ray photons, therefore more exposure to the patient? How much more? So it's going to be more than that. So again, the way you set this up, and I have a test, when we get to the test, I have a test question on this. So your MR is all on one side, and I'm sorry, your MA is all on one side, your MR is on another. What does MR mean? R stands for Röntgen, radiation in air, and we're talking about the radiation intensity coming out of the X-ray tube. Okay? So you set this up as an equal, two fractions that are equal to each other. So look at what happens, and you can pretty much see it increases about 2.5 times. So that's going to go up about 2.5 times. So very simple algebra, very simple algebra there. Any questions about that? If you have any, again, I have some practice problems with that, so work on them, and if you have any problems with it, my expectation is you'll get some help with that. Okay, so here is film screen. Here's what happens when you increase your MA, or you increase your time, or you increase your mass. Any one of those three things, this is what happens. So here I'm doing it with mass. So here's 10 mass, 12.5 mass, and 15 mass. This is looking at film. So you have a visual. I can immediately tell when I over or underexpose my image. The first one top left, the 10 mass is appropriate, 2.5 is okay, and then 15 is overexposed, meaning it's too much radiation and it's darker. You will not be saying over or underexposed in digital radiography, I'm guessing, because in digital radiography, it's going to look like this. In your textbook, go to page, I'm going to say it's 318 in mine. I don't know if it's in the edition. It's on digital radiographic technique. Is the now digital radiographic technique.
317.
Is it still 317? Okay.
Yeah.
Yes, looking at the foot X-ray. Yes, 317. So still the same page. Mine's on 318. 317. Do you see the foot X-ray? there's, if you look previous to that, there's a, instead of an abdomen, it's a foot, and it's one's light, medium, and and completely dark. And then look at the other page where you see 3 feet radiographs, and they all look the same. They're using the same technical factors for each one of those, and it lists what they are over there. And one is, it's like Goldilocks and the 3 bears. One is too cold, one is too hot, the other one is just right. Okay, but you wouldn't know that looking at those 3 images. They look the same, don't they? You know what it's going to look like if you use 10 masks, 12 and a half, or 15 masks? You know what it's going to look like? Yes. All 3 of them will look just like this. So why do you have to know what mask to use? What does it matter? Why can't you use 15? Why can't you use 50? Why can't you use 100 masks if they're all going to come out like that? Because why? It's your patient exposure. You're still giving your patient that exposure. So while you may not appreciate, I would have to repeat it. If I did this, I'd have to do it over. Okay? You will not ever have to repeat a radiograph because you used the wrong technical factors. You will never, your repeat rate for wrong exposure, 0%, 0. You will never repeat a radiograph because you used, okay, let's just say you used 100 masks for this abdomen. It looks like that. You wouldn't repeat it because you repeat it, it's still going to look like that. What do you do, though, the next time you do an abdomen image on a patient? Use 100 masks? No, you change it. You adjust it for your next patient. You don't keep using 100 masks. And how do you know? How do you know whether it's the right amount of radiation to use or not? Because visually, you can't tell. 100 masks would give you something even darker than this, but you won't be able to know that. How do you know? You will have a number on your image, an EI number, exposure index, or an S number, sensitivity number, that will tell you how much exposure was imparted to that image receptor. It's not necessarily the patient dose. The patient dose will probably be higher, but it gives you how much radiation energy was imparted to the image receptor, whether it's CR or DR. Okay, and so you have a range at your hospital that will say all abdomen radiographs will have an EI number between 100 and 200, or an EI number between 2 and 5, or whatever that manufacturer has for that system. There will be a range, not a precise number, but a range. You fall within that range, you're using the appropriate amount of radiation for that image. You're below or above that range, you're not using the appropriate amount. So what happens in reality in radiography? You use 100 masks for an abdomen, it looks fine. The next time you do and your numbers are going to be way off, and you're going to go, oh my gosh, my number is way too high. I need to back it down. You know, the next patient that you get, you might want to start at 50 masks, or ask somebody, what do you use for abdomen? What do you use for a hypothermic patient, for an asthenic patient? So you adjust after that. Okay. So changing your mass determines a bigger body part, more mass, more technical factors. So again, I thought I took that out. We're not talking about optical density anymore. Optical density is looking at the radiograph and going back to that. This is properly exposed, and this would be overexposed. We're talking about the density imparted on this piece of film. How much silver has been converted to black metallic silver. Okay, so we're not going to be talking optical densities anymore. Okay, so what does over and under exposure mean? Again, this is more of a film system. I don't know that we can ask your interns to see if they use this anymore. Looking at the image, you're not going to be tell if it's over or underexposed, but looking at numbers. See, from now on, you're going to be looking at numbers and not visually telling us if it's over or underexposed. That's gonna be the difference. So like right here, is that over or underexposed? This is properly exposed, so what would you say this?
Overexposed.
Overexposed, okay. By to that, you're not gonna have that anymore. You're gonna get two x-rays that look just like that. This one will be that way, this one will be that way. Which one's overexposed or which one's overexposed? You're gonna be looking at a number to determine which one is overexposed. So that's what you're gonna have to get used to. Okay, there will be a
It's the
number
EI,
that
right?
comes up on the control panel. When you take an x-ray, have you taken an x-ray yet? Do you have, is it in the lab room? Do you have a piece of, does anyone print out anything yet? Does anyone have it with them?
He gave us the big yellow thing.
Yeah.
He's in the car.
Oh, okay, and that's
Are you
fine.
talking about the film actual?
Yes,
there's a
on the
number on it?
monitor, you'll see it, but also when you print it,
Yeah, it's the-
there is a number on there, and I'll teach you in lab. I'll show you where that number is, and you will look at that and be able to tell if it's within range or out of range. And I'll also have the ranges for you. So right now, it doesn't mean anything to you, but at some point you're going to have a range. So let's just say this range is between 100 and 200, and every system has a different value. So when you go to the hospital and you're dealing with GE, it's going to be a different range than if you go to the hospital and deal with Philips
So it
equipment.
gives you a range also at the same time, plus.
It
or-
won't be on here, but there'll be, at your hospital, you'll have to find out what that range is. It'll be written down somewhere. They'll have pieces of paper maybe posted by the room. If you're doing a chest x-ray, it needs to be between, as an example, between 100 and 200. There's no unit. It is 100 and 200, 200 and 400, that sort of thing. And so you'll look at the number and it'll be printed on the image, and you'll look, and that's an excellent question. You'll look at it and go, I'm over or underexposed. You would never be able to tell otherwise. And that's what we're gonna do in lab today. We're gonna take some, and Thursday, we're gonna take some x-rays at different MAs and see if you can, and we'll be looking at those numbers and seeing if you can tell which one, has more, which one has less, and what they look like. So we'll be playing with it today.
So how about if we can manually adjust it on the computer so we can adjust the?
Yes, you can. You can.
Are we adjusting the number or what do you?
That's an excellent question. So the question is, okay, let's just say you take an x-ray. It looks perfect, right? But the number is out of range. So you can manipulate the image on the computer, right? You can make it darker, you can make it lighter. That doesn't change the number, so you can't fudge on that. The number stays the same. The number comes from the energy, X-ray energy imparted on the image receptor. So you can't change that number. So, and is someone standing over you looking at that? No, but radiologists are trained to look at that number. And if they're noticing every chest X-ray that you submit is over and out of that range, then they're gonna talk to you about that. So, but I would be mortified if you got to that point, that you can't do that on your own. Someone has to come and tell you to adjust your MAs or your mass because your numbers are out of range. And I tell you what, we got on to the interns, this was year before last. I asked them in class, I go, you are looking at your exposure index numbers, right? And they're looking at me like you are right now. I'm like, you better look at those numbers. That's part of your job, is to make sure you're within that range, that you're giving your patient the correct amount of radiation exposure for that body part.
With the AEC though, doesn't it automatically cut that off?
Very good. The AEC is, and we're gonna talk about the AEC, automatic exposure control, and that is, it should give you the appropriate amount. But it's not idiot-proof. You still have to set your parameters, and you still have to make sure everything is set appropriately. You still have to, if you remember about AEC, you still have to select your cells, activate the cells that you want for a chest X-ray, the outer two, not the middle one. You still have to make sure your patient's positioned properly over those cells. You still have to select your MA. You still have to select your KB, which you can still mess up on. So if everything's done correctly, then your AEC will work for you. So again, is this over or underexposed? This would be considered underexposed. Again, it's not going to look like this on CR or DR. You know, you can tell, okay, here's the issue, here's the problem. You can be overexposed up to 500% and you won't be able to tell a difference on the image, On the computer image, you won't be able to tell a difference. But you can only be 80% or less than 100% off your technique for it to be seen. And you know what underexposure looks like? It's grainy. Remember quantum model? Remember the term quantum model? I'm going to talk about this here in a few minutes, but quantum model makes your image look grainy. Quantum model occurs because you don't have enough X-ray energy to expose the image receptor. So when you don't have enough, it looks very grainy, and that obscures visibility.
That's like the
detail.
sprinkling, right? Like the
Yeah,
sprinkling.
sprinkle as opposed to a downpour. The sprinkling on the sidewalk, you can see the individual raindrops. We don't like that. We want it nice and smooth, like it rained and the whole sidewalk is covered with water. And so if you're gonna mess up, which way are you gonna go?
Over.
That's right. And we call that dose creep. We call that dose creep where we tend to go higher rather than lower. And so that's a problem with, again, patient exposure. And the theory is, if you double the patient exposure, what happens to the radiographer's exposure?
Double air exposure.
It's supposed to double also. If you were in the room with them, kind of thinking, where are we when we take an exposure? Typically, we're outside the room, but not always. So the theory is double the patient exposure, double our exposure to us. Not the same exposure, right? They're getting primary beam radiation, we're getting scatter radiation, but still the theory is there. So anything we do to reduce our patient's exposure, theoretically we're reducing our exposure. Okay, so MA and time. We typically like short exposure times. In radiography, we love, love, love our short exposure times. Short exposure times help reduce what?
Motion.
Motion. You have involuntary motion. You have doing an abdomen. You have peristaltic activity in the bowel that we can't control. Usually we say hold still, don't breathe, don't move. Well, you can't say that to peristaltic bowel movement. A chest X-ray for heart beating, you can't say, I'm sorry, stop your heart beating, during this chest X-ray. And so telling a baby who is moving, to hold still, they're not going to understand that. So we love our short exposure time because it reduces motion on our radiograph. Motion is the number one enemy of poor detail, or of detail. Okay, so now, here's the deal. MA and time is mass, we talked about that. The reciprocity law. The reciprocity law says it doesn't matter MA and whatever time, as long as it's the same mass, you'll get the same exposure to your image receptor. So if I told you, as an example, if I told you to use 10 mass for a chest X-ray, as an example, what are you going to use? I want you to go set your own technique, your manual technique, no AEC, no automatic exposure. I want you to set it. What MA are you going to select and what time are you going to select?
Shortest time.
Okay, I like it. Shortest time. So let me give you some examples. Let's just say your MA stations are 100, 200, 300, 400, 600. Okay, and I'm going to do time in seconds, just so it's easier for me. Something like that. Okay, what do you want to use? I want 10 mass. Let me throw that in there. Does that help? Okay, I want 10 mass. What do you want to use?
100 by 0.1.
Okay, we could use 100 at 0.1 seconds. What else? .400 at 0.025. 200 at 0.05. Will any of those give you 10 mass? That's the reciprocity law. MAS1 equals MAS2. Any one of those would work. One's better than the other two. Which one is better? The one with the shortest amount of time. Okay? Typically, your AECs may or may not do that. Select the MA and the time combination that gives you, we typically like high MA, shorter period of time. Okay? Because of the motion factor. Not all of our radiographs are like that. There are some that you will learn about this semester that we have a breathing technique where we want blurring. For instance, a lateral T-spine. The thoracic spine is through the rib area. So when we do a lateral T-spine, the ribs are in the way, the lung markings are in the way. And so what we do is we have the patient breathe during the exposure. It's different than what we normally do. So we have them breathe. The spine doesn't move. It's the rib cage that moves. It's the lung markings that move during the exposure. So they're blurred out and we just see the spine. Have you ever taken a picture of somebody while they're moving and it's blurry? That's what happens in X-ray. Okay, so there will be some times, not a lot, but there will be occasions that you want the opposite. You want a low MA and a long period of time. Okay, so the machine doesn't always set the MA and time combination that you may want it to. So that's something you have to think about when you're using a breathing technique or when you're using AEC. Do you want the shortest time? That's usually what the AEC does. If that's not the case, then you take it off AEC and do what we call a manual technique. You decide what MA and time combination that you want to use. Okay, but the reciprocity law is 10 mass is 10 mass. No matter what MA and time combination that you use. You have this is for film screen, so we can disregard this. The reciprocity law fails when you have extremely short or extremely long exposure times. So wouldn't your expectation be that 10 mass and 10 mass would give you the same, your images are always going to look the same. 10 mass or 500 mass, your image is going to look the same, right? It's going to be beautiful. But your numbers are not going to be appropriate. Your SI numbers or your exposure numbers are not going to be appropriate. So, so you would think 10 mass, no matter what combination I used here, then the number would be the same for all of them, correct? The expectation that the number would be pretty close to the same thing, okay? The reciprocity law states at very short exposure times or very long exposure times, a second, 2 seconds, 3 seconds, that reciprocity law fails. So your numbers may not be exactly the same when you're going to the extremes, okay? Some of your machines will go to 1/1000th of a second, which is about the shortest time that I know of. 1 millisecond. That's very, very short exposure time. So here are some examples, and this is what I'm going to give you for practice. We can do these in lab. You can take them home. We'll go over them next week. So here you have 200 MA at 0.25 seconds. What is that mass? You can use your calculators. You can do it in your head, whichever one you want to do. What is 0.25 seconds in milliseconds? So let's do the first one. What is that? If you want to use your calculator.
It's 50.
50
Yeah.
mass. What is this in milliseconds?
250?
250 milliseconds. And then what is this mass?
27?
27. Okay, so either change that to seconds or multiply these together and move the decimal 3 places to the left. The 3 zeros, 1, 2, 3, get rid of the milli part. So it's basically 9 times 3 is 27. Now, I don't mind you using calculators in here, not a problem until you get kind of used to these things and how it works. But out in the hospital, if you're setting your own technical factors, you're not pulling out a calculator. So we saw some pretty funny numbers in lab. We saw like, I remember 238 MA, and you have, I don't know, 170 milliseconds as an example. Hello, I can't do that. I might be able to with a calculator. I certainly can't do it in my head with a patient on the table moaning, oh, you know, oh, I hurt. Okay, I gotta hurry. Okay, so what mass is that? So one thing about mass is you just have to be, you have a range of numbers. You don't have a specific, oh, I've gotta be precise in the mass. You just have to get close. So I round that. I would round that up to down to 150, maybe that to 200, and that's something I can deal with a little bit better. 30, it's either 333 or 30 mass. I'd have to think about it a little bit more. But round it off, and you'll get close. Okay, so in real life, this is more of what you're dealing with than this. There are these stations, but then you get a lot of in-between things. So you can round off. Don't be afraid to do that. Here's one. Okay, so this is the reciprocity law right here. This is reciprocity. If 100 MA at 0.1 second was used to produce a diagnostic image, what does that mean, a diagnostic image? What does that mean to you? Do we like it? Do we not? Okay, it's an image. It doesn't mean it's a perfect image. It means it's good enough for the radiologist to make a diagnosis from.